So, so now we are going to go into bit technicalities. So the first thing that we want to discuss is how images are formed. So the basics of image formation, we are going to discuss how images are acquired, and and then we'll discuss about digital images mainly, because we are going to deal with digital images. So digitization involves something called sampling and quantization. So we'll discuss something about that. And then images can be represented as the digital functions, and there's some simple representation methods of images like a matrix representation. So we'll discuss a little bit about that. And if time permits, we'll also try to cover the different types of resolutions that are used for images and videos: spatial resolution, intensity resolution, and temporal resolution. And how resolution affects, what is the significance of resolution, higher resolution or lower resolution. We'll talk about that. So it's just a basic lecture related to image formation and representation. Okay, so so as you can see here that the basic process of image acquisition is like this. So there has to be some energy source, basically, which we call also which illuminates the object that or the scene that you're trying to capture. So the energy source has to basically illuminate the scene element with either light source. So it's not just our sunlight or visible light source. It can be other electromagnetic lights energy sources that we'll talk about. But the idea is that there has to be some energy source, and those energy rays or source basically when illuminates the scene element, and they get reflected. So some part of it may get absorbed by the element, by the object, because object itself has some absorption, some will have its own properties. So it will either absorb some part and reflect some part. So then the imaging system basically receives the reflected or the transmitted radiations from the object, and the images are according to, and then those transmitted rays are basically used for the formation of the image. So as I said, the illumination source need not to be a light source. It can be any electromagnetic modality. It can be X-rays, ultraviolet rays, infrared rays, or it can be even ultrasound rays. So we use ultrasound in medical imaging. So images can be formed by any of these modality. So basic about different electromagnetic spectrum. So we have a visible spectrum within 400 to 800 nanometer wavelength, and mostly what we see only in this visible spectrum. And but beyond this visible spectrum, there are other sections of electromagnetic spectrum. We have, if you go towards right, we have infrared, and then microwave, and these are increasing wavelength. So, and if you go towards the left, we have basically ultraviolet, X-rays, and gamma rays. Okay, within visible spectrum also we have a different wavelength. So, and each wavelength, different wavelength will have different color, because our light will be sensitive to that particular color in that wavelength. So the idea is that generally the principle of optics says that to resolve an object, we must use a wavelength which is either equal to the size of the object or smaller the size. So that means we may not be able to perceive all objects of all size and aspect with the same electromagnetic wavelength. We will need different different wavelength for to capture different types of objects, because this criteria needs to be met. So that's why we have to use different modality for capturing different source of different scene elements. So normally for as you go this side, for example, as you go towards the left, the wavelength is smaller. So for smaller size images, for example, if you want to capture or molecule or small particles, grain particles, and all that. So to have sufficient resolution, probably a visible light source will not be better. So we should use wavelengths which are of smaller size, so that we will be able to resolve those objects. The resolution will be higher in using that. So these are some examples of X-ray images. Normally X-rays are used for internal inside the body things, because X-rays have a higher energy. So you can see the energies of X-rays are higher. So they are able to penetrate surfaces, hard surfaces also. Of course, we cannot use gamma rays and all those things, because those will be injurious to the body. Even X-rays are injurious, not to a certain degree. So we can only do it to a certain extent. So different molecular level imaging generally has to be done. We use gamma rays and all that for things. And when we go for remote sensing and astronomical objects, we use microwaves, radar, and radio waves. So radar, for example, radar images uses microwave wavelength, and other telescopic and other things may uses radio waves to capture images. And then there are other modalities. They have their own uniqueness also. For example, infrared imaging has a uniqueness that it can work in low light conditions. So for example, visible images are only good as long as there is a sufficient sufficient illumination. If it is a night time or if it is a low light situation, our visible image will not be able to see a lot of things in there. But infrared imaging works well in imaging in low light situation, especially because there are infrared also. We have near infrared and far infrared. So there is called thermal infrared imaging. Thermal infrared imaging are very sensitive to heat of the surfaces. So they are useful for example, for detecting for people, because people generally, our body temperature is generally a higher temperature than the surrounding environment. So you can see the person generally they get easily captured in an infrared imaging, even in a night situation. Whereas in normal visible camera, you may not be able to see the object as clearly as in an infrared image. So many of the military devices and all this, they are equipped with infrared. Some of the cars, some of the high-end cars, they are also use infrared cameras, so that in low light situation they can see the obstacles or any person, pedestrian in the way. Similarly, so that's why when you talk about images, we are not only referring to normal visible range electromagnetic images, but images can be any. When we talk about digital images can be a radar image, it can be a X-ray image, it can be a PET image, it can be infrared image, whatever. So as far as visible imaging is concerned, visible spectrum imaging is concerned, the imaging devices will have at least three major components. One will be your image plane on which the actual image will be formed. So this image plane will be either consisting of an array of sensors, or it will be coated with a photosensitive surface, which will get excited by the light rays which get incident on that surface. But apart from that image plane, there will be some kind of an optical system, and there will be some kind of an aperture. If this is the object that you're trying to capture image, so first of all there will be an aperture. The role of aperture will be basically it allows it restricts a certain amount of light only to pass through. So aperture will have a whole kind of thing, so it will allow a certain amount of light and with certain angle only to come inside. because if you don't restrict the images, if you don't restrict, if light sources fall from all directions, then the the image that will form will be very blurred image. So in order to restrict that, in order to form a sharp image, there is an aperture which basically restrict only lights raised from certain angle and certain amount only to be incident on the optical system. And then there is an thin lens optical system whose task is again to focus the light on the focal plane of the image plane. So that that lens is also required for forming a sharp focused image of the object. So little bit we'll just discuss in brief about this. So again, image formation is a detailed topic, sometimes discussed in a lot of details, but we don't want to discuss it here because it is mostly useful for optics and other people, for hardware, for device people. We are basically more interested in the algorithm part and the application part. So just basic idea is sufficient. So we'll talk about two parts of the image formation process. One is the geometry, which basically relates to where exactly the a real world scene will be formed at what coordinate, the location of the point. So it determines where in the image plane the projection of a point in the scene will be located. So where a particular real world point scene will get projected on the image plane, that is basically the geometry of the image formation. And the physics of the image formation basically refers to the brightness and the brightness of the how bright that image will be. So that will depend on the illumination and the reflectance of the surface. So surface properties like reflectance and so on. So just a brief of the geometry. If you want to understand the geometry, a simplest way to understand is if you consider the pinhole camera model. So in a pinhole camera model is basically a very rudimentary imaging device. You can have basically a cardboard or a box and have a small hole here and one side, and on the other side you basically coat with a photosensitive surface. And if you keep this box in a dark room so that only limited amount of light passes through, and if you keep an object there, you can see an inverted image of that object will be formed on the photosensitive surface that you have of that pinhole camera. So here basically the lights are incident from in this way. They will pass through this aperture. So this is the small aperture that you have created. If you increase the aperture size, then multiple rays will basically get incident and your image will get blurred. So you have to make the hole very sharp hole, a very small hole. Then only the image will be little bit focused or sharp. So if you consider this, if you consider a real point P here with coordinate x comma y, maybe let me just have capital X and capital Y. So this point on the top of the head is getting projected at this location on the image plane. So let us say this is point. This is the image of point P dash with small x and small y coordinate on the image plane, and so the distance of this object from the camera aperture is, let us say, z. So this distance is probably z, and the distance of the image plane from the aperture is f, which is basically the focal length. Then you can use this similar triangle formula. So you can use this similar triangle basically. So you can see that this, I'm not able to form that similar triangle here, but maybe let me draw it separately, then it will be easier. So let us say this is, here you have an object. Let me draw it on us, and here you have an image plane, and this object is basically forming a inverted image here. And let us say this is capital X and this is small x, and this is your basically your aperture or lens, and this is your focal length as z. This is the distance of the object, and this is your focal length f. Then you can use this two similar triangle to basically come with this relationship. So small x upon capital X will be equal to small f upon capital Z. So that gives you x equal to f times x upon z. Similarly, if you see it, this is on a one, I'm just seeing a one-dimensional thing. So if it is in 2D, you will get the similar equation for the y also. Of course, this for the simplest camera holder model. If there is a lens, then you have to have a different thing there. Is this clear? Any question on this point? Anybody has? So same thing we can basically. So just an example here. So if you consider our eyes also like a pinhole camera, then again you can calculate the size of the tree, the length of the height of the tree that will be formed on the retina using the simple similar triangle equation. So you can calculate this very easily, I think. So if this is this is z, this is f, and this is x, you can calculate small x using the previous equation that we have derived. Another specification generally that is given for any camera or imaging device is called field of view. We generally any camera, if you see its specs, one of the specs will be the field of view of the camera, whether it is a wide angle camera or it is a or how much is the field of view. So generally, because that field of view helps to determine how so if you can see this example here, this diagram here, and imagining this as image plane is this of that device. So if h is the total size of the image plane and f is the focal length, then if an object at a distance d, how far that can be seen is this. So this object, this point will form, and so here we are the image plane, instead of putting it at the back, we are putting it here just to keep it inverted. So this is one of the standard way we do it. Instead of doing an inverted image thing, we bring the image plane here itself, so that the same image forms an upright manner here. So the same thing is being shown here. So if you see, otherwise you can just consider the image plane here also, that doesn't matter. So this object somewhere here, this point in real world will form a point in the image plane at the corners. So in this image plane, if it is the image plane is going to have a certain dimension. So here, assuming the size of the image plane is h, so at the topmost point or the bottommost point, this pixel image, this real world scene will be projected at this location. Okay, and now anything beyond this will go off the image plane. So it will not form any projection on the image plane. So that's why this field of view is specified, because the camera can only see within its field of view. So this theta field of view can easily be calculated using the focal length and the image plane height things. You can easily calculate the field of view, and with the field of view you can know how, if you are looking at a distance d, how wide that camera can capture, how wide the scene that camera can capture. Beyond that, you cannot capture. You will not be the scene will not be captured in the image plane of the camera. So that is also one of the important specs. Some images have higher field of wide angle field of view. Some cameras have smaller angle field of view. Generally, camera also have variable focal length. So you can adjust the focal length. So if you want to see far off things, you can increase the focal length. If you want to see nearby, you can have a shorter focal length. So if you have a wide angle field of view, you will have a shorter focal length. You cannot have a larger focal length at the same time. So that trade-off is there. So those are related to camera specs and all that. Just for your practical information, if you're going to purchase a camera, you can, these things are important specs that you should think about depending on your requirement. So if you are going to use a camera for a image processing application or computer vision application. So for example, when we had to use camera for our classroom, so we have to go for a wide angle camera. If you want to capture the entire camera scene in just one camera, then we have to go for a wide angle camera which has probably 180-degree field of view, or as large as possible 120-degree field of view. So those specs are needed to be aware of when depending on application and depending on your requirement. Okay, so as I said, normally in your actual camera, you will have a thin lens instead of a single aperture. The problem with an aperture, if you just using an aperture, is you cannot make it larger, because if you want to admit more light, you have to make it larger. But if you make it larger, then there will be diffraction happening and all that. The images will be getting blurred. So to avoid that, generally we use a thin lens. Thin lens has the property that it can converge the light rays which are parallel, and they will pass all through the focal length. So the thin lenses have those characteristics. So that's why we use thin lenses in the cameras. And actually we use multiple lenses, not just one single lens. We use a combination of lenses so that to make it variable so that you can adjust focal length and all that. But in that case, the equation changes. So now you don't have no more that same similar triangle equations. Again, you can use the similar triangle equations to derive the equations, and I hope you would be remembering from your physics this equation: 1/f is equal to 1 upon v plus 1 upon u. That thin lens formula. So that you can derive again using the similar triangle. So if using u, v, and f, you can derive this equation. And again, you can figure out the geometry and the location, the coordinates of the real world, and from the real world scene to the image coordinate, you can use these equations to calculate those values. As far as the physics was concerned, the photometric thing was concerned, there are different models. The simplest model says that the intensity value of the image will depends on the illumination. So at any point x comma y, the amount of the illumination that is happening at that point, which is we are representing by I x comma y, and the reflectance of that point. R is the reflectance or transmission. So if it is an X-ray, then it will be transmission, and if it is a normal visible light or something, we will call it reflectance. So how much that point is reflecting the surface property at location x comma y, if you represent it as r x comma y, and the illumination source, the illumination property as I x comma y, then the resultant intensity that will be formed will be basically a simple multiplication of illumination and the reflectance. So if you want to have a higher intensity image, your illumination should increase, or the reflectance of that point should increase, or both should increase. Okay, so normally your illumination can go from 0 to very large value. It can go up to infinite, but in practically it will be some small value, some fixed values, some range, and your reflectance will generally reflectance of different objects or different surfaces range from 0 to 1. So 1 means it will fully reflect it, and 0 means it will absorb everything and reflect nothing. So that kind of scenario also may happen. So some objects generally tends to absorb everything and reflect nothing. So in that case, you basically get a black point there or black image. So if you're generally there is a numerical at the end on this sometimes, but so I will not talk about that. I will leave that exercise. So just your practically your I will range from some I minimum to I max. Similarly, your R reflectance will also range from some R min to R max value. So as a result, your F x comma y will range from I min times R min and I max times R max. So that is how your image different locations in your image at different xy locations will have values, minimum values this and maximum values this, and then this range again normalized between 0 to 255 or depending on how you are representing your image. So if you are representing your images using 8 bits, so minimum you can represent it 0 and maximum value you can represent is 255. So this range again has to be renormalized between 0 to 255. So that is done by the imaging device itself before you get your final image. Renormalization happens again at the device level. So we'll talk about that when we discuss the resolution in more detail. In your digital camera, normally earlier we had used to have analog camera, but nowadays they are practically extinct species. So, but you almost have only digital camera, so no point talking about analog camera. In digital camera, generally we have a sensor array. So instead of a photosensitive surface or photosensitive film, we have basically an array of sensors, and in that array, in each cell is basically kind of a light sensitive diode, which basically converts the incident photon to electrons. So each cell will be basically kind of a light sensitive diode. There are two types to this. One is called charge coupled device diode, and other is called CMOS. CMOS are more recent one and they are more better quality. CCD was the earlier standard. So what basically when energy rays falls on that thing, generally first there is a filter, some kind of color filter is there, which basically filters out some part of the color and only absorbs the other part of the energy, and then it basically converts that light sensitive diode basically converts that photon into electron. So you basically some voltage gets generated, and that voltage is basically received by the electrical device to convert that voltage to some representation, some numerical representation, and then that way basically images are represented. So that is the inside of how for camera. And this camera, as we said, depending on the type of imaging equipment, that the placement of the sensors can be different. So as in camera, generally in a normal visible, your normal handycam or all your mobile cameras and all that, generally you will have an array of sensors, a 2D array of sensors. So each cell will be basically a CMOS or CCD kind of a cell diode, and it will basically be arranged in a two-dimensional pattern, and that's why you get an image, a 2D. Actually, you get a we'll see you get a color image, but right now we are just talking about the grayscale thing. But in other imaging device like your scanners, in your scanners generally we have just a single strip of sensors. So you have just a single strip of sensors, and your sensors are basically arranged on that sensor strip, and this sensor strip basically translates in one direction. So when you start the scanner process, you can see the scanning happens from one end. The scanner strip basically moves from one end to the other end. Or in your Xerox machine also you can see that. So by combination of this mechanical motion and this arrangement, so your sensors are already arranged in this direction, and because now your sensor strip is moving in this direction, so it basically images the entire area. So it basically minimizes the cost. So instead of having the full 2D array of the sensors, you are having just one single strip of a sensor, and by doing this mechanical motion, you are able to capture the entire 2D area of the object or the document and so on. In your medical imaging devices, generally where you need a 3D cross section of the image, for example in your CT scan and other kinds of things where you take a 3D cross section, there may be a different arrangement of the sensors. So for example, here in one of these brain imaging device, generally we have this circular sensor array. So we have an array here, we have this sensor ring. So the sensors are coated on the inner side of this ring, and now your object which has to be imaged, basically this object it is basically moved inside this ring, and this and then this energy source, there will be an energy source like an X-ray source here. This X-ray source itself will be rotating around that object. So by rotation of this X-ray source from the energy, the cross section, the entire 3D surface of this object will be basically get imaged, will get projected on the sensor ring. And also because we are doing this linear motion, so this subsequent section, so in once of so you will get this kind of image cross section of images will be generated. So this entire combining this cross section of images, you will be able to get the entire 3D projection of this object. So anyhow, that is all detail. You don't need to understand all this thing, but just for your general knowledge, these are the different types of sensor arrangement which are there. In order to capture color, color images, generally what is done, apart from your 2D arrangement of sensors, there is a filter also put before every sensor, and those filters are generally 3 types of filters: color, red, green, and blue filter. So the idea is that each color will only filter will only let that particular color. So red color will block all the other color rays, and will only allow the red light to pass through it. And in order to make the arrangement cheaper, instead of for every pixel having all these 3 filters, the way it is done is basically each cell will have only one particular type of filter, and they are basically arranged in this particular arrangement, which is called basically called Bayes array. So you see here in this arrangement, I think we have the number of green filters are more than the number of red and the blue ones. This is because of the property of our human eye. In human eye, the cones are the sensors which are responsible for color perception, and amongst them also the majority of the cones are the majority ones are sensitive to the green light, and the red and the blue are less majority. So because that is the way human situation is there, so people have come up with this arrangement which is best perceived by human eye. The images obtained by this kind of an arrangement is best perceived by the human eye. So that's why this particular arrangement is generally found in most color cameras. So you can see the green ones are the majority ones, and adjacent to every green there is one red and one blue one. So the idea is now, because for every pixel you will need its red component, green component, and blue component. We'll see talk about later that every pixel or every single value will have 3 channel values: red, green, and blue in the color image. So, but because now we are using only one filter at each location, so we are only for at every location we are either getting either it's only green, blue or red values. We are not getting all three values for each location. So what generally is done, this is followed by some kind of an interpolation. So using the adjacent green and blue values, some interpolation is done for the green and blue value for this location. So for this location, you already have its green value, but the red and blue value is not available. So to calculate the red and blue value, the adjacent red and blue values are used, and those values are interpolated. And that way, you basically get a color image. So it's basically tries to optimize cost and still get the best possible color reproduction. So I think we'll stop here rather than going forward. So we have just basically discussed about very general information about cameras and image formation and all that. In the next class, we'll talk more about the digitization aspect. So because we are going to talk about digital images, so how digital images are represented, how sampling is done, quantization is done, and how it affects the quality of the image, and those things we will discuss in the next class. If anybody has any question on this